Welcome, students. We want to talk about Green's theorem today. Before that, I'll read this quote by Alexander Grothendieck. He was a well-known algebraic geometer. Discovery is a child's privilege. I mean the small child, the child who is not afraid to be wrong, to look silly, to not be serious, and to act differently from everyone else. He's not also not afraid that the things he is interested in are in bad taste or turn out to be different from his expectations, from what they should be, or rather, he is not afraid of what they actually are. He ignores the silence and flawless consensus that is the part of the air we breathe, the consensus of all people who are or are reputable to be reasonable. Okay. So with this quote, we start with Green's theorem. So what is Green's theorem? So Green's theorem can be thought of as a generalization of fundamental theorem of calculus. So note that if you have integral a to b f prime x dx, then this is same as the antiderivative of this evaluated at the endpoints. Essentially, what you're doing is you are integrating your derivative on this interval, and this amounts to calculating your function values at the boundaries, right? So these are the boundaries, right? So you compute the difference of the function in the boundaries, right? So we want to have a similar setup for line integral. So suppose you want to evaluate this line integral. So this line integral over this curve C, which is the boundary of D, has connection with certain integral on double integral over D. Okay, so this is the connection. So let's see. So let C be a positively oriented piecewise smooth curve. So positively oriented means it is the region D lies to the left of the curve when traced. Say for example, this will be negatively oriented, right? Because here the region lies to the right of the orientation, right? So let C be a positively oriented piecewise smooth. Piecewise smooth means corners are okay. Yeah, so corners are fine in this case. But this piece, so it's a collection of piecewise smooth curves. Yeah. Simple closed curve in the plane, and let D be the region bounded by C. So you have this region D, which is bounded by C. If P and Q have continuous partial derivatives on an open region containing D, so if you consist of any open region, and P and Q has partial derivatives which are continuous on this open region D, then the line integral over curve C of P dx plus Q dy is dou Q by dou x minus dou P by dou y dA. Okay. So this is what the Green's theorem is. All right. So now we'll soon see what kind of derivative does it relates to, right? So it's like you're looking at the antiderivative of this, and it turns out doing some evaluation on the boundary of this curve. Okay. And the notation is, since the curve is closed, so since your C is closed, we will write C P dx plus Qy as integral over curve C P dx plus Qy dy. Okay. So this is the Green's theorem. Now let's use this theorem. So let's use this theorem, use Green's theorem to evaluate the line integral of Ey dx plus 2x e to the power y dy, where C is a square consisting of sides x equals to 0, x equals to 1, y equals to 0, and y equals to 1. So let's draw this region. So the region is, so if you look at the region, x equals to 0, x equals to 1. So x equals to 0, x equals to 1, this is 1. So x equals to 0 is this line here, x equals to 1 is this line, y equals to 0, y equals to 1. So use Green's theorem to evaluate the line integral where c is a square with sides, and we should say c is oriented counterclockwise. Counterclockwise. Okay. So again, let me do the orientation here. So this is the orientation. This is your C, and the region it encloses D is the following. What is D? So D is essentially this square where x is between 0 and 1 and y is between 0 and 1 as well. So the Green's theorem tells us that if I want to compute this integral, I can compute this double integral. Okay, so computing this line integral is equivalent to computing this double integral. So let's compute that. So let me write down the notation. So here we have p dx plus q dy over curve C is same as double integral over region D, dou q by dou x, partial derivative of q with respect to x minus partial derivative of p with respect to y dA. So p is your p of xy is e to the y, and q is 2x e to the y, right? So then the right hand side is equal to, the right hand side becomes integral over d. Now since it's a rectangle, we can choose Fubini's theorem to write down iterated integral in any form. So I'm going to choose first with respect to x, then with respect to y. What is dou q by dou x? Dou q by dou x is 2 e to the y. What is dou p by dou y? Is e to the y. And the region of integration for x is 0 to 1. So x is going from 0 to 1, and y is also going from 0 to 1. So 0 to 1. And then this becomes 0 to 1, 0 to 1. So we can separate them, dx, e to the y, dy. This is going to be x 0 to 1, e to the y 0 to 1, which is going to be e minus 1. So our integral I turns out to be an easy computation of e minus 1. Now note that it has saved us, in some sense, Green's theorem has facilitated the computation here, because otherwise you will have these four curves, C1, C2, C3, C4, I mean all the boundaries of the square. You would have to compute the line integral. So you had to compute 4 line integral, and now we are able to do it just by computing one double integral. So this is how Green's theorem helps us. Okay. So, I mean, again, I mean, like we may you go either way, right? I mean, to compute the double integral, we may use line integral and vice versa. So it would be a reasonable thing to see a proof of this. So let's see the proof of it over a rectangle. So consider, so let So let's take a rectangle. So without loss of generality, we'll try to prove it on a rectangle first. So let F be a vector field Pxy, Q of xy, a continuous vector field. So it's continuous vector field. We have continuous vector field on D. Actually, it should be continuous on an open interval, open set containing D, and let delta D be the boundary. Okay, so delta D is the boundary, which is our curve, which is same as C for us. Now we want to prove the Green's theorem for this. So need to prove the Green's theorem. So what we'll do is we will compute the integral on curve C f dot dr. Now the way we are going to go about it is we are going to parameterize each of C1, C2, C3. So C1 f dot dr plus C2 f dot dr plus C3 f dot dr plus C4 f dot dr. Now let's write down the parameterization for each of these. So C1, what is the parameterization for C1? So C1, let the parameterization for C1 be. So C1 is this piece of curve here, from here to here. And the parameterization of C1 is parameterized by, say, R1 T, which is simply, so your Y remains fixed as C, and your X is T. T goes from A to B. Similarly, you have C2 parameterization. So parameterizations, let's write down the parameterizations. So C2 is this curve here. C2 can be given by R2 of T, which is essentially your X is fixed as B, and we get Y to be T, and T goes from, again, C to D, right? So T goes from C value to D. Similarly, we have C3 as R3T. Again, parameterization is given by, in this case, again, Y is fixed as D and X is T, where your T goes from, so T ranges from where to where? So T ranges from here to here, right? So T ranges from C, so from B to A, but we want to now write it down properly. So what we'll do is we will call this as minus C3. Okay, so now minus C3 can be given with the opposite orientation. So minus C3. And in that case, my T will go from where to where? A to B. Then we have, so this is R3 is for minus C3, not for C3. Okay. Similarly, we have C4. We'll again take minus C4. Minus C4, the orientation is given by R4 of T, which is given by, again, we have in this C4, we are looking at minus C4, so minus C4 will be in the other direction. So minus C3, this is minus C3, and minus C4 is going to be in the opposite direction, right? And minus C4 is given by your X is fixed as A, and your Y, so X is fixed as A, and your Y is T. Again, your T goes from C to T. Okay. So now let's compute the line integrals now. So we have, so I'm going to write it down as C f dot dr is going to be C1, F is going to be PQ, but P, for P, instead of X, I will have T, but instead of Y coordinate, I will have C. Then same thing as PTC, QTC dot dr1 now. So I have dot dr1. What is dr1? Dr1 is going to be derivative of this with respect to t. So it's going to be 1 comma 0 dt. Now let's continue with the C2. So C2 is going to be, again, in this case, the parameterization is, so P, instead of X, I have B, instead of Y, I have T, instead of Q, I will have Q of BT, and dr2 is going to be what? Going to be 0 comma 1 dt. Let's keep continuing this. So now for plus, so it was now plus C, right? So now I'm going to write minus C. So minus of minus C. So it's going to be minus C3, right? Minus C3, because integral of minus C3 is minus of C3. Okay, so we get minus C3. We have, again, in C3, we have the parameterization as follows. Parameterization is C3 is, instead of X, I have T. Instead of Y, I have D. And dr3 of T is going to be 1 comma 0 dt. And the last one, again with the minus sign, for the same reason, because we are going other way around, minus C3, C4, my bad. In that case, the parameterization is P of A T, Q of A T, then dr4 of T. So that is going to be 0 comma 1 dt. These are dot products here. Okay. Now note that I could have already written now. So my T goes from here. In the first case, my T goes from A to B. In this C2, we have T goes from C2, T goes from C to D. In minus C3, T goes from, again, so minus C3, T goes from A to B. And here for C4, minus C4, we have this goes from C to D. So now let's rewrite this integral. So we get integral A to B. So if we take the dot product, only the first term survives. So PTC dt. plus C to D P, sorry, Q will survive. So QBT dt minus integral A to B, here PTD will survive dt minus integral C to D QAT dt survives. So these are the objects that survive. Now I can bring these two together. So I'm going to bring this guy and this guy together. So this will be integral A to B P of TC minus TD minus P of TC dt. I'll explain in a moment why I chose the minus sign there, plus integral of integral of C to D Q of BT minus QAT dt. But if you look at the inside object here, this can be seen as essentially, you can keep the minus A to B out. Now this can be seen as partial derivative with respect to y of P T y and integral from C to D with respect to what? With respect to dy, then dt. And similarly for this guy here, if you look at the inside part, it can be written as C to D. So this can be written as partial derivative of Q with respect to X. You integrate that with respect to X, you get Q, and then you put the limits from A to B dt. Now, instead of dt, we can call it X, right? So let's call that as X. We get minus A to B minus C to D dou P by dou Y, P of xy dy dx plus C to D A to B dou Q by dou X dx. Instead of in this T, we'll call it Y. Okay, now combine these two integrals together. We get A to B, and we can change the order of integration, right? Because it's a rectangle. Yeah, using Fubini's theorem, we can change that. A to B, C to D. Now this had a minus sign, remember? Now we can write it other way around, dou Q by dou X minus dou P by dou Y, and bring dy dx outside. Or, well, d, so first is dy and then is dx. So this is essentially integration over d. So we have proved the Green's theorem. This is your d. For a very simple case of a rectangle. Okay. Now note that this same kind of idea can be extended to a more general region by breaking it into certain pieces, right? All right, so now let's use the Green's theorem to evaluate this line integral f dot dr, where f is the following, where c consists of arc of sine x from 0 to pi 0. So here, so let's extend this. So we have sine from 0 to pi 0, and then the line segment joining this guy. So we want to evaluate this line integral. So now we'll use Green's theorem, and the way we'll go about it is as follows. Note that this is not oriented counterclockwise. We need a counterclockwise orientation for the Green's theorem, right? Positively oriented means counterclockwise orientation. So how do we go about it? Instead of finding for the curve C, which is, this is C1, C2, so we want to compute integral of C, and your C is basically, your C is C1 union C2. What we'll do is as follows. We'll basically do C2 to C1, right? So let's do this one now. So integral over curve C f dot dr is integral over curve of minus C with a minus sign f dot dr, right? So we are changing the orientation. So minus C is going to be in the so this is what your minus C is, right? So minus C is in the other direction, in the positive orientation, right? So now this is going to be minus of integral, double integral over region D f. So instead of f, this line integral turns into a double integral, and your double integral is dou p by dou y. Sorry, it's the other way around, right? So q first, so dou q by dou x minus dou p by dou y dA. Dou y dA. So we are already given p and q, so this is going to be integral minus d or region D dou q by dou x. So derivative of this with respect to x is going to be 2x minus derivative of this with respect to y, p with respect to y is going to be 2y, and then dA. Now it's a good idea to write down the region now. So we'll write down the region as y first, because it's y simple. So y goes from 0 to sine x, and x goes from 0 to pi. So x goes from 0 to pi. Let's write it down slightly so that we have a proper representation of this. So we have x goes from 0 to pi, y goes from 0 to sine x. 2 can be taken outside, x minus y dA. So we are doing y first, and then we are doing x. So this can be seen as minus 2, 0 to pi. We have integration of x with respect to y is xy minus y squared by 2, 0 to sine x dx. Now that can be written as minus 2, 0 to pi, x is going to be, so xy, so x sine x minus sine square x divided by 2 dx. And the computation shows that this is going to be minus 2 times 3 pi by 4, which is going to be 3 pi by 2, which is minus sign. Okay, so for first part, you can use by parts, and then this sine square, you can convert it into 1 minus cos 2x by 2. So this is your line integral. So as you notice, the fundamental theme here is we are using Green's theorem to convert your line integral into a double integral. Now the other way around is also interesting. So consider the following. So you have a curve C, positively oriented, and the region inside is D. This is a region D inside it. Now, over this curve C, suppose I integrate x dy, then x dy by Green's theorem is going to be double integral over D is going to be dou q. So this is your q, right? So dou q by dou x minus dou p by dou y dA, which is going to be double integral. Dou q by dou x is 1. Dou p by dou y, there's no p. So p is essentially 0 here, dA. So dA, which is essentially area of this region D. So now you see line integral basically gives you the area of region D. This is the idea behind the planimeter video I've posted. So planimeter uses this concept to compute the area of enclosed by a certain boundary of the map. Okay, pretty cool. So similarly, you can see that minus of this y dx, in this case, this is p, is again, if I use Green's theorem. So this is using Green's theorem. So if I use Green's theorem again, it's going to be integral d y, so minus of, so here p is y, so 0 minus dou p by dou y, which is going to be 1 dA, which is again going to be integral, which is AD. Or if you take this integral, half of line integral over curve C, x dy minus y dx, this is going to be half double integral. So in this case, your p, this is your q. So dou q by dou x minus dou p by dou y dA. And again, we get half dou p by dou x is over region D, over region D. Dou q by dou x is going to be 1. Dou p by dou y is minus 1, so minus of minus 1 dA, which is again going to be integral, which is A of D. So in all this setup, you see that you can use either of these line integrals to compute the area enclosed by the curve C. Pretty neat. Which one to use? Well, I mean, it's up to you. Whichever is easy to compute is the one you'll use, right? Okay. So let's look at the following problem. So find the area enclosed by one arc of this arch of the cycloid, x equals to t minus sine t, y equals to 1 minus cos t. So how is one arch of cycloid given? So one arch of cycloid is essentially given by this, where t goes from 0 to 2 pi. So we want to compute the area under this one arch of cycloid, which is given by this. So we can use either of these formulas, x dy minus y, or y integral of y dx, or so on and so forth. So I'm going to use the following. So here, let's give an orientation to this. I'm going to use area equals to close integral over curve C. C is, this is C1, this is C2. My C is C1 union C2. And I'm going to use y dx. Why is that? Because, well, for C1, what is the parameterization? So C1 is given by 0 for y, and t for x, where t goes from 0 to 2 pi. And C2 can be seen as, we'll change the parameterization because we have a clockwise parameterization. So C2, so I'll parameterize minus C2. So minus C2, again, so minus C2 is going to be t minus sine t, 1 minus cos t. T goes from 0 to 2 pi. Yeah, again, the reason for this parameterization is because then I'll have t going from 0 to 2 pi. Otherwise, my t goes from 2 pi to 0, and that's not really good looking, right? So now let's see. So this is my area. So area is going to be minus of, in bracket, C1 when y is, so here I get y is 0, right? So y becomes 0 dx. I don't care what dx is, y becomes 0 right away. Then I have C2, so minus, so integral over C equals to C1 plus C2. But now if I use the negative the other orientation, I get C2 with the minus sign here. So this will become minus of C2 f dot dr. So what is my y? My y is basically going to be, this is my y. So y is 1 minus cos t. And what is my dx? My dx is going to be 1, 0 dt. So dx is going to be derivative of this guy. So dx is going to be derivative of, this is my x here, right? So this is the x. So dx is going to be, again, 1 minus cos t dt. And this orientation, so I have minus to take care of. So I have minus C2 now here, right? So the first part becomes 0. The second part is integration of C minus C2. Now minus C2 goes from 0 to 2 pi. 1 minus of this minus and this minus will cancel out each other. We have 1 minus cos t, the whole square dt. So then we have 0 to 2 pi, 1 plus cos square t minus 2 cos t dt. Now we can write this as, so if you look at this integral, 0 to 2 pi. So let's write it as 1 plus 1 plus cos 2t divided by 2 minus 2 cos t dt. And when you integrate it, you will get all signs, and 0 to pi will basically kill all of them off, except you'll be left with what? You will be left with t. So you'll be left with what? 1t plus t by 2 going from 0 to 2 pi, which is going to be 3 pi. Okay. So this is the integral of, so this gives you the area as well. So this is your region D, and you have computed the area using the Green's theorem. So I should have said that area, this is due to what? Due to Green's theorem. So whenever you're using Green's theorem, we should mention that. Okay. Now let's look at the following again. So integral of y squared dx plus 3xy dy, where C is the boundary of the semi-annular region D in the upper half plane, x squared plus y squared equals to 1 and x squared plus y squared equals to 4. So C is the boundary of this semi-annular region D in upper half plane between the circles. So inside circle is x squared plus y squared equals to 1, and this outside circle is x squared plus y squared equals to 4. And we are giving a positive orientation, that is counterclockwise orientation to it. And we want to compute this integral. So we have C integral C y squared dx plus 3 dy. So let's call this region D, which is this annulus. Piece of annulus. So this guy here, we have P, we have Q. So this integral, line integral I, so this integral is going to be integral over this semi-annulus region using Green's theorem. So by Green's theorem, let me write that down, Green's theorem. So by Green's theorem, this is going to be dou Q by dou X, which is 3y, minus dou P by dou Y, which is 2y dA, which is going to be integral over region D of y dA. Now region D, we need a plan for region D. We want to do double integral. Note that region D in polar coordinate looks much better, right? So in polar coordinates, your D is simply r theta, where your r goes from 1 to 2, right? And your theta goes from 0 to pi. So it becomes a polar, it's a polar rectangle. So my integral I is going to be, instead of y, I have r sine theta. Instead of dA, I have r dr d theta. Now let's go r first. If you go r first, you got r from 1 to 2. You go theta from 0 to pi. We can really separate these integrals now. So this is going to be 0 to pi of sine theta d theta and 1 to 2 of r square dr. So first integral is going to be minus cosine theta 0 to pi is going to be r squared by 2, 1 to 2. And this is going to be, so cos of minus cos of pi. So the first part is going to give me 2. The second part is going to give me 2 square minus 1 square by 2. That is going to be 3. So this is the line, this is the line integral you're trying to compute. Again, see the beauty of Green's theorem, right? It helps you, instead, otherwise you will have this 1, 2, 3, 4, right? So 4 parameterization and you have to work it out. Now, because of Green's theorem, you can just compute the area, right? I mean, like, sorry, the double integral over region D, okay? All right, so next step is for a slight extension of Green's theorem for doubly connected region. So let's try to understand this scenario. So let R be a doubly connected region with one hole, doubly connected hole in a plane. So let's see, we have a region R. So outer boundary C1 is counterclockwise, and we have a hole inside, which is C2, which is hole oriented clockwise. If the boundary curves and f of x satisfy the hypothesis of Green's theorem, then the idea is you have integral of C1 plus C p dxy, p dx plus q dy, plus line integral on this closed curve C2 of p dx plus qy is same as Green as a double integral of dq by dx minus dp by dy dA. So you see, it's an extension of Green's theorem, really. So how do we prove it? So we'll perform a surgery here. It's quite a common tool, actually, in slightly more fancier topological methods. So we'll perform a surgery. We'll cut it into 2 pieces like that. So this one has an orientation of perform a surgery like that. So we have, so this part will be, let's call this as D1 or R1. I'm gonna call it R1. Let's call this as R1. So this whole region is R, by the way, the annulus region, right? Let's call this as D1. Let's call this as D2. Now let's see, what is the orientation of D2? So D2 is also goes, okay. So now we have the following. So double integral over region R, dou q by dou x minus dou p by dou y dA, because the areas, the integral, double integral is additive over 2 regions as long as they only overlap in boundaries. We have d1 dou q by dou x minus dou p by dou y dA plus over region d2 dou q by dou x minus dou p by dou y dA. Now what we need to do is, so orientation has to be proper, right? So, well, we have the original region was oriented counterclockwise. So here also it's counterclockwise. Now, so for this one, we have counterclockwise. So here also it's counterclockwise, but it will basically coincide with, so let's have this thing with this direction for the other part. Okay, so we have the following. So this is going to be, let's give this piece's name. So let's call this as, let's call these pieces of curve by some names. So we have, or so let's call this piece of R1, sorry, this piece of, let's call this piece on top as A1. Let's call this piece here as A2. Let's call this direction as A3. And let's call this direction as A4. All right. So now what do we get? We get for D1 is going to be integral, line integral containing the region D, but when I write it in terms of, it's going to be C, it will be A1 union A3 union A4, right? A1 union A3 union A4 of P dx plus Q dy, right? So A3 union A4, but what about this piece here? So let's call this, again, we have one more piece left out. So we call this as, so this is oriented in, so let's call this as A5. So union A5. So this is the first part of D1. Plus, instead of D2, I'm going to write, now how does my D2 is composed of? So D2 starts with, so we can think about D2 as A2, then, so D2 goes like that. So A2, then you basically are going in the opposite direction of A4. So union minus A4. Then we are going to take this one here, which is going to be, let's call that part as A6 now. So this part is A6. We have A6 union A6 union A6 union minus A3 P dx plus Q dy. Now, if I wanted, or if we wanted, we could have made arguments simpler by basically calling these as in the other direction. So they cancel out. Okay. So this is your C1 is in the other direction. So this is your direction of C1 is this one, and the direction of C2 in the other one, right? We call the outermost one as C1 and the innermost as C2. Okay, so we could have done the cancellation business. But I just want to point out things explicitly here. So we get here, in this case, we get A1 union I can write A1 union, I will break this as A1 plus A3 union A4. Then I'll have union A5, 1, 2, 3, 4, 5. For the first part, again, it's P dx plus Q dy, so I'm not going to write that. Plus, going to break it as A2 plus minus A3 union A4 minus. Then I have plus A6. So now when you do this, these two guys will cancel off each other because they are same sign. These two ones, A1 and A2, will combine to give you integral over curve C1, and A6 and A5 combine to give you integral over C2. So this basically proves the result. Of course, this is a rough proof. So the idea is, if you have a doubly connected region, R is connected with one hole, and note that the outside one is counterclockwise and the inside one is clockwise. Okay, so the orientation have to be different. Then we have, this is given by the double integral. So now, what is the beauty? So let's look at nice application of this. So suppose we have F, again, a continuous, so F is a vector field, has problem at 0, 0, right? So we wanted to compute this. So now what we want to show is that if you take any positively oriented simple closed path containing origin, any, right? So let's take any positively oriented simple closed path enclosing the origin. Origin is here. Let's call this C. Then we want to show that this f dot dr equals to 2 pi. Yeah, that's pretty neat, that no matter what, yeah, you will basically, as long as you enclose the origin, any continuous positively oriented simple path that encloses the origin, the integral line integral is 2 pi. So again, we'll use this method here. So what we'll do is we'll draw a circle here, oriented counterclockwise. So we'll orient this circle counterclockwise. So let's call this as a circle C. So we'll orient it clockwise, right? Because the outside curve is counterclockwise, inside is clockwise. So C. So C can be any circle. So you may say, well, I mean, if we need to, we are not sure what will be the radius of the circle. So where C is a circle of radius epsilon, yeah, where epsilon can be as small as we want, right? So that we can guarantee that it will lie inside the C. So now, what does Green's theorem, sorry, the extension of Green's theorem for doubly connected region tells me? So, but note that if I orient it like that, maybe I will have the proper orientation for circle comes with the negative sign. So let me just basically, you know what, let me change the orientation and have, instead of this, I will have a orientation like that for C. Okay, so C is a circle oriented clockwise, anti-clockwise, yeah, positively. So that means what? That means minus C will be oriented in the clockwise, right? So now what do we have based on the previous result? We'll have integral along the curve C of f dot dr plus, so integral along, so this was C, let's call this as C1, so this is minus C1 now, plus integral along minus C1 f dot dr is equal to double integral over region D, where D is this region between D dou P, the dou Q by dou X minus dou P by dou Y dA. Now note that we already have proved that for this guy here, if you take P is minus, so P is going to be minus Y over X squared plus Y squared, and Q is X over X squared plus Y squared. So we have already proved it. This is a very interesting example, right? Because it's not a conservative vector field on. So, but we have proved that dou P, dou Q by dou X minus dou P by dou Y is 0. And how did we prove that? We computed dou Q by dou X. If you apply the quotient rule, you'll get X squared minus Y squared upon X squared plus Y squared the whole square minus same thing equals to 0. So this would mean, this would imply that the integrand here is 0. So we get C f dot dr plus minus C1 f dot dr is 0. Now, this means if we bring it on the other side, we get C f dot dr. This will be minus of C1 f dot dr, which will be, well, minus these minus will cancel out. We have integral of C1 f dot dr. Now we are in business, right? But now what is C1? C1 is a circle. So now again, I'll apply Green's theorem here. So this is going to be what? This is going to be f dot dr over, so we have, what is r of t in this case? So we want to compute this now. So C1, let's do a parameterization for C1. So C1 is going to be, so C1 is a circle of radius a or epsilon here. So C1 so parameterization for C1 is r of t, which is epsilon cos t. Note that epsilon is fixed, huh? Fixed. This is fixed. Fixed. Fixed enough so that it lies inside there. So epsilon cos t, epsilon sine t, t goes from 0 to 2 pi. So now we get, this is our r of t. So we have integral C1 f dot dr is going to be 0 to 2 pi. Now what is my f? F is minus yx, right? So minus y, which is minus epsilon sine t over epsilon. So what is upon x squared plus y squared, right? So x squared is going to be epsilon square cos square t plus epsilon square sine square t, which is going to be epsilon square. So epsilon square, here we'll have epsilon cos t divided by epsilon square. And what is my r prime? My r prime is going to be epsilon times minus sine t. Then I have comma epsilon times cos t dt. Now if we combine this, so we get 0 to 2 pi, we'll get epsilon by epsilon square sine square t plus cos square t dt. And that is basically integrating 0 to 2 pi of dt, which is 2 pi. And voila, here we are done. Okay. So, well, the key idea was using Green's theorem for the doubly connected region. Thank you for your attention.